Good evening and welcome to the Exploratorium and to this evening's presentation of Everything Matters, Tales from the Periodic Table. Tonight, we have made it all the way to element 11, sodium. So sodium actually is a big part of our lives, so we're going to talk about some of that tonight. It's actually a really large subject, much larger than I thought it was going to be. I'm going to talk a little bit about sodium, a little bit about its chemistry and its physics, and then I'm going to be followed by John Largier, who is a professor of coastal oceanography at the University of California, Davis. He's also a scientist in residence here at the Exploratorium and helps us out up in the Fisher Bay Observatory. And he's going to talk about saltwater and freshwater and how that operates in our local bay and how it affects the ecosystems in our bay. So I hope everybody got their collectible card. Did you get your sodium card? It should have been on your chair. And I hope that you all got your collection of cards. I'm afraid we may be out of hydrogen now, but you never know. That might get reprinted if you come to a future Everything Matters, Tales from the Periodic Table. But we're now up to the 11th card, beautiful card designed by our graphics folks upstairs, the really wonderful cards. And we hope you collect them all. Just out of curiosity, how many people here in the audience have more than sodium? Raise your hand if you have more than just the sodium card. So people who have been here more than once. Cool, okay. How many people have everything starting at hydrogen? Oh, there's a few people, wow. Very impressive. Okay, I just have to fix something here on my presentation. Sorry about that. There we go. So when we start off with sodium, of course, we always have to start off with the periodic table of the elements. Now we're up to 118 of them. That was new news last month, all the way up to element actium, right there, actium, just discovered in Dubna, Russia. And so that doesn't have a real name yet, so actium 118 is the name of it right now, and they will figure out what to call it in the future. Sodium is way near the top of the table. It's element number 11. You can see it's going to zoom out there. There's element sodium. It is a kind of a pretty element. It's actually a silvery, very soft silvery metal. And we'll see some of that metal a little later on. It was originally called natrium. One of its chemical compounds was called natrium, which is really sodium carbonate found in nature. You don't actually find metallic sodium in nature because it's so reactive. It just doesn't exist as a metal in nature. You have to actually make the metal and refine the metal. Sodium carbonate, by the way, that natrium is where the Na came from for the chemical symbol of sodium. Sodium's chemical symbol, Na. But it's also known that sodium carbonate as soda ash, and that's where we got the term for sodium, the name sodium. So the name sodium and the chemical symbol are a little bit different. It was first synthesized by this fellow, Sir Humphrey Davy, and it was in 1807. For some reason, my presenter notes aren't showing up here. Maybe I can make that happen here. There we go. Okay, 1807. And he synthesized sodium by taking apart one of its chemical compounds, specifically sodium hydroxide or caustic lye. So here's caustic lye, sodium and an oxygen and a hydrogen. That's sodium hydroxide. And the way he did this was he melted this, and he put a set of electrodes nearby, and he charged one of the electrodes negative, one of the electrodes positive, and if you have enough of a charge, enough voltage there, you can tear apart sodium hydroxide, and the sodium collects on the negative electrode and the hydroxyl on the positive electrode. So you get a bunch of sodium collecting on one electrode, which you then scrape off. You have to be a little careful about that, of course, because sodium is so reactive. As far as nature goes, sodium is about the 9th most abundant element in the universe. If you look at the sun, it's actually about the 15th most abundant element, and as we'll see later on, you actually can see in the sun spectrum that it does show up. We move to the crust of the Earth, I found some arguments as to whether it's the 6th or 7th most abundant element in the crust of the Earth, but about 23 grams per kilogram of the Earth's crust consists of some form of sodium in compound. And if you look at the oceans, of course, you might suspect that the oceans are actually, it's the 4th most abundant element in the oceans, with about and then if you go in humans, in your body, there actually is quite a bit of sodium. It's the 9th most abundant element in your body, of course, in the form of sodium, mostly sodium chloride in your blood, salt water. Sodium has a lot of different forms. Well, we've talked about this in previous talks, where in the nucleus of sodium there are 11 protons and a variable number of neutrons. And if you look at that, all those ones with variable numbers of neutrons are called isotopes. As long as there's 11 protons in the nucleus, it's sodium. But there can be 11 protons and 12 neutrons, and that would be 23 total particles in the nucleus. That would be sodium-23, and that is the only stable non-radioactive form of sodium. So basically, it's 100% of the sodium on Earth is sodium-23. Sodium-22 is actually kind of cool. When it decays by spitting out an antimatter particle. It's a positive electron called a positron, and it's used as a source for positrons, for instance, in CERN, where they put together positrons and negative nuclear particles to make antihydrogen, which they've done very recently. They use sodium-22 as the source of the positron. So kind of cool. 20 isotopes of sodium. All of them are radioactive except for sodium-23, and all of them have fairly short half-lives except sodium-22 and sodium-24, which last on the order of days. Sodium, surprisingly, the density of sodium is pretty low. It's 0.968 grams per cubic centimeter. That is less than the density of water. Water has a density of 1 gram per cubic centimeter, which means that sodium floats. It's a metal and it floats on water, which we might get to see. Sodium is made inside of very large stars, primarily, and it's made by a process where it burns carbon. Most stars burn hydrogen. We've sort of seen that in some of the previous talks, but sodium is made by burning carbon. In this process here, you take 2 carbon atoms, carbon-12, that's kind of our common form of carbon we have here on the Earth, and you combine, you smash 2 of them together, and you create a sodium nucleus and a hydrogen atom as well. So that's how sodium is made, but just in big stars, because this requires extremely high pressures, extremely high temperatures greater than 500 million degrees. That's much hotter than in our sun. You need a much bigger star that produces much higher temperatures inside of it, so the atoms are moving much faster and they smash into each other with much more energy. And you need, again, a much more active star. Big stars do this. Stars that are 3 to 9 times the size of our sun. So sodium, if you look at it again in the periodic table, it's all the way over on the left-hand side. It's part of a group called the Alkali Metals. Lithium, we've already covered lithium before. Lithium, sodium, potassium, rubidium, cesium, and francium are all those alkali metals. Hydrogen doesn't quite fit in there. Hydrogen can actually fit either above that column or above the fluorine column, the halogens, which we did a couple of months ago. So we're just going to leave that out. We're not going to call hydrogen an alkali metal. If you check out, remember from a couple of months ago, we looked at the atoms of the halogen group, that vertical column over on the right-hand side of the chart, and that included fluorine, chlorine, bromine, iodine, and so on. And they're interesting in that they have outer electron shells that are sort of missing an electron. If they just had one more electron in their outer shells, they would look like the next column over. They would look like noble gases. So here you can see that there's a little notch. There's one missing electron in all of those outer shells. And if they had those electrons, and they would look like this: helium, neon, which we did last month, and argon. Notice those have complete outer shells. These guys are happy. They are very happy. They don't want to add any electrons. They don't want to give away any electrons. They don't want to form any chemical compounds with anybody. They're the noble gases. Fluorine, chlorine, bromine, iodine, those all would like to steal an electron. They chemically are super active. They want to take an electron from something. Today, the group that we're talking about, the alkali metals, are sort of almost the opposite of those, the halogens that we were talking about just earlier. Here, you notice that lithium, sodium, potassium, they have a shell on the outside with only one electron. They would love to get rid of this electron. If they could get rid of that electron, they would look just like a noble gas. They'd be happy. So these guys really like to give up their electrons. As a matter of fact, they combine real well with the halogens. As a matter of fact, if you take one of these things, like sodium, and a halogen like chlorine, you'll notice that the sodium has that extra electron it wants to really get rid of, and chlorine has a little spot for one. It really would like to grab it. And indeed, if you get them close enough together, they do. The chlorine will grab onto that electron from the sodium, and that makes see, if you take an electron away from sodium, you don't take the proton, you just take the electron away. That leaves the sodium positively charged, and the chlorine, now that it has an extra electron, is negatively charged, and opposites do what? They attract. And so click, now you have a molecule of sodium chloride, or salt, which we're going to talk about a little bit here. So that's an ionic solid. Hydrogen was a small atom. We've looked at hydrogen every month. We compare it to all of the other sizes of all the other atoms. And last month, if you remember, neon was a super small atom. But because of that extra electron, just add one electron that's loosely held in the outer shell. Sodium is this huge, humongous atom that has this electron hanging out there just waiting to be taken. As a matter of fact, we talked a little bit about electronegativity. The electronegativity is a chemical property, and it describes the tendency of an atom to attract electrons to itself. So high up in this chart means I want an electron. Low down in that chart means I want to give one up. And you can see sodium is really, really low on the chart there. It really wants to give up an electron. Fluorine is way up on the chart just before sodium there, right before to the left of the blue line there. If you excite sodium, which you can do in a flame, do this at home. Take some of this stuff and unbend a paper clip and lick it and put some salt on it. And then go to your stove, and I'm assuming this is you have a gas stove, not an electric stove. I can't do this at home. Go to your gas stove and put that salt into the flame. You'll notice a bright yellow flame will come from it. That bright yellow is from the sodium. It gives off a spectrum of a really bright color sodium. As a matter of fact, here is on the top there is the spectrum of sodium. It only gives off yellow light. There's two lines that are really, really close together there. Just for reference, the bottom is the hydrogen spectrum. But you can see it only gives off this yellow light. And we can use that. You can use this in lamps. As a matter of fact, here is a low-pressure sodium lamp, and you can find this inside the Exploratorium. There's an exhibit that you can just walk just across the central gallery, the Bechtel Central Gallery here. It's an exhibit that's called the monochromatic room. Mono, because it only puts out one color. Yellow. We're using low pressure sodium vapor lamps in there. The only color that you can see inside that room is yellow, because that's the only color of light in there. Here's the low pressure sodium lamp lit up in the room over there. And if you look at stuff in the room, there's a bench in there that has all these beautiful colored swatches on it. But with the sodium lamp, you can only see shades of yellow. So there's no color here at all. You can see dark yellow or light yellow. That's it. If you shine a white light on that same bench, though, here's what you see. That's what the bench looks like. Want to see it again? Sodium light, white light. There's a whole bunch of crayons in the room, too. Here's what the crayons look like in the sodium light. That 64... That box of crayons you always wanted as a kid with 64 crayons with a sharpener, you know, the Binney and Smith, yeah. You wouldn't want it if you only lived in sodium light. But if you had white light, hey, all right, cool. So you can see spectrum in the, you can see sodium in the spectrum of the sun. The sun's spectrum is a little different than what I showed you. I showed you that spectrum that showed you the bright colors of light given off by the element. But elements can absorb the same colors of light that they give off. And that's what you see when you look at the sun's spectrum. The surface of the sun gives off white light, all colors. It's hot, it's dense, and it's like a tungsten lamp. It gives off all colors, a continuous spectrum. But the outer atmosphere of the sun is cooler, and that cooler atmosphere can actually absorb colors of light specific to certain elements. So here's the sun's spectrum. Now, this is kind of stacked up. This would be hundreds of feet long if I showed it all in one little strip. So these are a bunch of strips kind of stacked up. This was taken at Kitt Peak Observatory near Tucson, Arizona. And you can see these dark lines crossing the spectrum of the sun. Those dark lines are due to various elements in the sun's atmosphere. So you can tell what the sun is made of without going there and taking a scoop of sun and bringing it back to the lab. This is a really useful tool. So look at those two yellow lines there and there. Those are caused by sodium. There's a couple more lines that are interesting here too. I can just point at them. This line right here, this dark line here, that's caused by hydrogen. These green lines here, these dark ones are caused by magnesium. That's another hydrogen line down there. And there's all kinds of lines in there. You can see that the sun has calcium and hydrogen, and interestingly enough, helium was discovered on the sun before it was discovered on Earth. Hence its name helium, after the sun god Helios. There is no helium in the atmosphere of the Earth. We actually mine it. So it comes from underground, and so you have to get helium. And it's a non-renewable resource. So using it in party balloons, shouldn't do that. Use hydrogen, it's much more fun. Now this is sodium at low pressure. It absorbs or emits a very distinct set of colors. But if you raise the pressure in a lamp like this is a high pressure sodium lamp. Looks kind of the same as the low pressure sodium lamp, admittedly. But the spectrum is quite different. Here on the top you see the spectrum of high pressure sodium, and on the bottom you see the spectrum of low pressure sodium, which just has those yellow lines. And there is an exhibit here at the museum where you can actually experience that. We have this spectra exhibit also over on the other side of the Bechtel Central Gallery here. And in there is a high pressure sodium lamp, and you can see the spectrum of high pressure sodium right there. So, there's lots of chemistry involved in sodium. There's so much chemistry, there's no way I can actually talk about all of it. There's so many chemicals that sodium participates in, so much chemistry that it's really hard to kind of wrap your head around. We can talk about a few things up here. I mean, here we all know sodium chloride is salt, and up here we have a lot of really great salts. You might want to come up after and take these salts, maybe sprinkle a little bit. You might want to try this mesquite smoke flavored salt. That's actually kind of cool. But there's all kinds of salt. There's the Kalahari desert salt. There's Celtic sea salt, which I love the marketing on these things. Taste the salt, recommended by health professionals and culinary chefs. Really? Okay. Doctor recommended since 1976. Marketing on parade, okay. Salt, of course, is a really common form of sodium that we can find all over the earth. There's, of course, that soda ash, the sodium carbonate that I was talking about a little bit earlier. This stuff here, baking soda, or this stuff right here, baking powder, that has sodium bicarbonate. That's the NaHCO3. What else do we have up here? Oh, we have Drano. Drano has sodium hydroxide in it. That's the NaOH over on the left-hand side there. We've talked in the boron, if you were here for boron, the Na2B407, that's borax. So if you ever use that really great soap, that's what's in it, borax, sodium borate. Sodium nitrate, NaNO3, you can use that as a nice oxidizer, explosive. What else do we have up there? Oh, we have CH3, now I don't know why CH3COONA has the Na on the other end. I'm not a chemist, so I need a chemist to tell me why it occurs on that side of the formula instead of the normal side of the formula. That's sodium acetate, and that actually has a cool thing associated with it as well. Here I have, you've probably seen these some people may have seen these hand warmers. They have a liquid in them. That liquid is sodium acetate. And there's a little metal disc in the middle here. Can you see that little metal disc right there? Maybe we should get the camera close up on this. Chris, you want to get a close up on this? This is kind of cool. If I snap that disc, this is in a supersaturated solution here, and if we snap that little disc, it'll cause this to start crystallizing, and when it crystallizes and turns from let me see if I get the disc in the middle so you can see what it's going to do here. There we go. Okay, I'm going to snap the disc, and then we're going to, okay. Did it do it? And it didn't do it. Let's snap the disc again. There it goes. It's crystallizing, and the heat of turning from a liquid to a solid actually makes this into a really quite wonderful hand warmer. Want me to do it again? I'll do it again. Here's one I did the other night. I turned it back into liquid. Okay, here we go. Having trouble getting the disc. There we go. Okay, here we go. Isn't that cool? A sodium acetate. So these are actually quite, I'm going to pass them around here. They're quite warm. So anybody who has cold hands, you'll be happy to get this. So sodium chloride, that we're all familiar with, of course, salt. I really wanted to get a big block of salt here, but it was just a little too expensive. We didn't feel that we could spend $50 on a block of salt up here, so we'll have to settle for the cows. And the cows are great anyway, I mean, really. Salt is really one of those things that we encounter early on, and it's one of the first things that I encountered that I observed was a crystal. Because you could look at this stuff under just a magnifying glass, and you notice that this stuff is just all these little cubes. That was quite a thing when I was a kid to notice that. I guess one of those things that geeky science kids noticed anyway, that there's all cubes. Very cool. Now that actually is useful. Salt actually has other uses other than just for flavor. And it actually played a crucial role in forming temperature scales. Temperature scales? How do you form it? How do you make a temperature? How do you make a thermometer? You can make something that shows changes in temperature, a thermoscope, but a thermometer, a thermometer, actually lets you measure it. It has degrees. How do you make a thermometer? It's very simple. How do you make a temperature scale? First, you have to find something that everybody can make that's cold. So something everybody can agree on, everybody can make it, but that's cold. You take your thermoscope, you put it in there, the mercury or the alcohol, whatever is in there, goes down, you scratch the thing, now you have a cold mark. Then you also need something that's hot. You put your thermoscope in there, the mercury or the alcohol goes up, you make a scratch. Now you have a cold point and a hot point that everybody can agree on. Now, you just have to decide how many marks to put between the cold point and the hot point. So you need degrees. Once you've decided how many degrees to put between the cold and the hot, you're done. You've made a temperature scale. You've made a thermometer. Who's done this? We know the guys who did this. Gabriel Daniel Fahrenheit was one that we know about because we all still use his scale here in the US. Anders Celsius was another one of those guys. We use his scale here too. And what did they do? They had to have a cold temperature and a hot temperature and a number of degrees. And here they are. So on the left here, you see the Celsius scale, and on the right, the Fahrenheit scale. And we all know that Celsius used what as his cold temperature? He used the freezing point of water. So he made a mixture of ice and water. the thermometers went down, he scratched it, and then he put it in boiling water, they went up, he scratched it, he put 100 marks between, Celsius scale. We also called that the centigrade scale for a long time, not anymore. Fahrenheit was a little different. Fahrenheit said, you know, I can make things that are colder than the freezing point of ice. I don't want to deal with negative numbers. I want to start my temperature scale at the coldest thing I can make. Now, that was, you know, back in the 1600s, they didn't have liquid nitrogen. The coldest thing, what would be you can make things that are colder than ice. How do you do that? Let me give you a clue. The answer is somewhere on this table here. How do you make things that are colder than ice? What does this thing say right here? It says ice cream salt, rock salt for ice cream and cooling. If you mix salt and ice together, the salt gets in the way of ice crystals forming, and it actually lowers the temperature of the solution. So brine freezes much, much lower. As a matter of fact, when Fahrenheit did that, his temperature scale went down, and he put a scratch there, and he called that 0. 0 Fahrenheit is as cold as you can get with a mixture of salt and ice, a brine mixture. And we use that fact. We use the fact that salt lowers the melting point of ice, and we use it in de-icing. So you can de-ice a plane by putting salt on it. It'll lower the temperature of the freezing point of the ice. It'll come off of the airplane. You could put it on roads, and it will keep the ice from forming on roads. Of course, this only works down to a temperature of 0 degrees Fahrenheit, because below that the brine freezes. So you can only do this at between 0 and the freezing point of ice, fresh ice, which is at 32 degrees. And so de-icing, salt is something that's used for de-icing very commonly, which is why on the East Coast, where they use a lot of it on the road, the cars rust out because you get all that salt water underneath your car. Salt water rusts things much more readily, as we here at the Exploratorium are experiencing as well. Sodium is used in making of glass. So all this green glass and brown glass, it's called soda lime glass. There's sodium used in the production of the glass. This stuff here, Drano, has sodium hydroxide, caustic lye in it. But you'll notice that it also has little chips of aluminum in it as well. And those, you may have noticed if you've ever used Drano, that there's metal chips in it. And those metal chips are important. When you put Drano into your drain and add water, the caustic lye reacts with the aluminum, and the aluminum chips get hot. And if you're trying to dissolve a clog that's made of grease, it really helps to get the grease hot, because it softens the grease and makes it easier for the Drano, which is mostly sodium hydroxide, to do its work. There's other chemicals in there to dissolve hair as well, but that's getting a little further than we want to go. Now, using sodium hydroxide in grease also does something else, which we also have on the table up here. If you use sodium hydroxide and a little bit of heat, you can turn the fat in your drain into this stuff, bars of soap. Well, they don't turn into bars of soap, but they turn into soap. And that's one of the processes in that chemical process that sodium hydroxide is used for. Sodium hydroxide and heat will break apart those chains of molecules, attach a sodium to the end of the chain. And that sodium end, by the way, likes to be in water. The other end is the greasy end, and it doesn't like to be in water. The sodium end is hydrophilic, and the other end is hydrophobic, and that's one thing that helps soap break the grease off of your hand. So soap, or sodium stearate in this case, is made with sodium. One cool application that, well, not so cool actually. One interesting application that sodium is used for is to cool reactors. Now this reactor actually hasn't been built quite yet. There are reactors that use sodium for cooling. This is kind of a prototype reactor. And here you can see the reactor core. I'm going to step off the stage again, use the pointer. The reactor core, which is right here, is generating a lot of heat, and it's heating and melting this pool of sodium right here, which then gets pumped out and into a heat exchanger right here. There's water in this pipe here, and so the water gets vaporized and is used to drive a turbine here, and that turns the generator right here. So the water never touches the sodium, and we're going to find out why in just a moment. But using sodium actually has some advantages. Sodium melts at a fairly low temperature, 98 degrees C, so less than the boiling point of water. But it doesn't boil. Water boils at what? Water melts at 0 centigrade. Sorry, I was educated earlier than I should be. 0 Celsius, and it boils at 100 Celsius. It has a 100-degree range. Sodium melts at 98 degrees C, and it boils at 883 degrees C. So there's a huge range in there. You can heat sodium for 785 degrees. It's a huge range. So it's fairly useful as a coolant because it has such a large range. Where water only has a 100-degree range, sodium has a 785-degree range. It doesn't absorb as much energy to raise its temperature, sodium. It actually about a third. It takes about a third as much energy absorbed by sodium to raise its temperature by a degree than water. So water is a better cooler, but it has less of a range to it. Sodium makes up for it with its larger range. Sodium also has some additional advantages, as this reactor doesn't have to be pressurized because you never vaporize the sodium. The temperature this reactor works at is always at a temperature less than the boiling point of sodium, so you never have to pressurize the containers. That's actually kind of a big advantage. Also, sodium is a good conductor of heat, and it's a good conductor of electricity, which means you can pump sodium using using no moving part pumps. You can pump it electrically, and that's actually pretty cool. And the last thing is that sodium doesn't corrode parts, metal parts, like water does. So there's a lot of advantages to using sodium in a reactor. So kind of an interesting use of sodium, melted sodium metal to actually cool a reactor. So I've been talking about sodium and water and the fact that you don't want to let the two meet. So we've gotten to that part now. You're ready, Chuck? Okay. So this is the part you've been waiting for. But first, you got to do the chemistry. So if I add sodium to water, so Na plus H2O, here's what's going to happen. It's going to turn into sodium hydroxide, which is lye. It's a very basic substance, and it's going to give off hydrogen and a lot of heat, So this is the reaction we're interested in. If you did it to a lot of sodium, which we're not going to do, you get large reactions. We're not going to do that kind of size reaction because this kind of scares the hell out of me, to be honest with you. But there have been very large reactions with sodium, and I found this great war film. During the war, sodium was used, and they had to dispose of a lot of it after the war. And so this is a great post-war film here.
20,000 pounds of highly dangerous metallic sodium head for destruction in Lake Lenore, Washington. The government surplus chemical ignites.
This is before the EPA.
The Alkali Lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium trickles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions. The acrid clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Assets Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
You gotta love it. Again, like I say, obviously before the Environmental Protection Agency. I was actually kind of shocked. I don't know if I should tell you this, but I was actually kind of shocked. I was kind of searching around online. There actually is a place you can buy sodium online. It's called explosivemetals.com. What can I say? Okay. So I wanted to do that little experiment on a small scale for you because it's kind of an interesting little thing. I have some metallic sodium over here, and we might want to have our, I'm going to get some gloves on because I'm going to show you the sodium. And I'm going to give a set of glasses to Chris. Do you want to help, Stephanie? Just in case I need some help, get some gloves on? Okay. There we go. And got to get my screwdriver out. So I got to open. I have it in the paint can here. This is from an exhibit that we were building decades ago, actually. So I keep it in this can, and in this can, since sodium reacts with just about everything, you have to keep it under oil. So here is a piece of sodium. This is what it looks like. It's actually fairly light. It's all corroded over. So what I want to do here is I'm going to, I need the chopsticks too, eventually here. Can you unwrap those? I'm going to cut it. It's very soft metal. You can cut it with a butter knife. So I'm going to cut a little piece of this sodium metal off of this. You'll notice I'd be able to cut it just with a knife. See how bright and look at how shiny that is. Those little holes are what we punched in there when we were building the exhibit. So I'm going to take a little piece of this. Let's put that back in the can. And I'm going to take a little piece of this. That's probably enough. And I'm going to put the top back on the can, and we're going to move the can away because I don't want the kerosene to be anywhere near anything that's flammable. We do have a fire extinguisher that's specially built for metallic fire. So in here, I have water, and I've actually put a little bit of indicator in the water, and that may change color, and there's a pH strip right here that we might be able to see change color as well. And to do this safely, I want to put a shield around it because it generates enough heat to melt the sodium, and if there is a little bit, it also generates hydrogen, and if it throws things around, I don't want molten sodium to be thrown out into the audience. Okay, so I'm going to cover it with this. So I'm going to grab that little piece of sodium there. So let me just... I'm going to throw it in the water here. Are we ready? You ready, Chris? Here we go. I'm going to throw it in right. 3, 2, 1. Now, there might be a little pop because it is generating sodium, and if it catches fire... Now that's from sodium on the top lid here that it kind of blew out. Let's just leave that on there for now. And okay. I think we're good now. That's why this kind of scares me a little bit. Okay. So if you have any questions about sodium, please feel free to come up and ask. No, you cannot have a piece to take home with you. Thank you all for coming. And I hope you stick around for the second part of our talk with John Largier talking about salinity of the bay and why that's important to us. Thank you.